Welcome back to Hacker Hangouts on an unusual time on a 2:30 on Saturday, but we are excited because we're jumping in, downloading RAM. It's a thing now? Like, it shouldn't be. It's been the internet meme forever. But you were describing to me, you can download RAM, or at least maybe in the near future.
Yeah. Oh, you want to share my screen real quick? I'll show you.
Yeah, absolutely. Here, I'll flip on over to you and I'll make myself just a little bit smaller.
Yeah, so here we are at downloadmoreram.com, and you can, scroll down and select a plan here. And I want to select 32 gigabytes of additional RAM, and there you go.
Gosh.
We're downloading more RAM. This is classic. I love this website. But no, this is it's kind of a joke, but not really. So there's this new technology, and here you see we've initialized it, and now we have to go here for more info, and there you go. We've downloaded more. So that was a Rickroll. Go to downloadmoreram.com to get more RAM. Have some fun with it. But so the real situation here is there's this new technology coming onto the market called CXL, Compute Express Link. And rather than go read the 900-page specification like I did, and continue to read it, rather than do that, you can just listen to me for the overview. Functionally speaking, CXL is a build off of PCIe. So it's PCIe based. Everything is PCI based. So eventually these devices that we're going to talk about today are just going to be PCI cards, or they're going to be devices connected over PCIe links. And, right now it's PCIe 5.0. It'll eventually become 6.0, all of those things. But there was an idea, I don't know, over a decade ago, and Linus Tech Tips actually has this on their website or their YouTube channel from a few years ago. I think it was Gigabyte, or I forget who it was that actually built this card. There was an idea a long time ago. What if I just put RAM on a PCIe card and put it on the PCI bus? And they did that. And they actually put, some number of gigabytes on a PCI card. And I mean, this is before the days of PCIe Express. They just flopped it on the PCI and they called it a memory expander. I think at the time they called it something else. But now that idea is stuck around. And today you can go out and buy PCIe memory expanders. They're relatively expensive, and so is the memory you plug into them, because I don't know if you've looked at DDR5 prices lately, but
it's
kind of crazy.
Utterly ridiculous. So I'm at pause though, because this has been a project you've been working on, and I've heard the internet meme forever. I even Linus Tech Tips totally had you can actually download more RAM, and I went and watched it because I'm curious. And it wasn't really more RAM. It was swap space, just having a lot of swap space and using Google Drive and mounting it as swap space. That is not what you're talking about here. We're talking actual RAM.
We're talking about actual RAM, right? And so and for anyone who doesn't really know what swap space is, it's a file that you can allocate on your hard drive, and then the operating system will just kind of put old memory into that area and then bring it in at a later time as you start exhausting memory. So it's like pseudo RAM. It's not RAM, right? It's really, really slow. And so this is where it gets really important. If you want to share my screen again, I'll show you.
Hold on, you're getting into talking that. I kind of want to ask. Anytime I set up a slide deck, which I know all of us I have my 32 slides.
How are we going to download more RAM? That's what you want to know.
More simpler than that is it's always problem, case study, and then what is the solution? So why do we need to download more RAM?
Okay.
Why is this even a problem?
This is actually exactly why I wanted to bring up this just a very short slide. I promise you this is not going to be a slide deck show of a podcast, right? And I'm going to explain this for our listeners. But right here we have what we call the memory period. And CXL memory is on here. But at the very top, you have these the components of a processor is a register. And registers are very small in size, maybe 8 bytes, maybe 16 bytes if you're using vector things. They get bigger, maybe up to 128 bytes, right? And that, to access it is very, very fast, 0.2 nanoseconds, right? It's absurdly fast. It's hard to actually fathom how fast 0.2 nanoseconds is. Then most people know you have L1 cache, L2 cache, L3 cache. all of those things. And then you have your main memory. This is your DDR4, DDR5 on modern PCs. And the scale of just going from register to main memory is 0.2 nanoseconds in a register, all the way up to 140 nanoseconds in RAM, right? So that's already like what what is it times 10, right? I can't even, the words are hard this afternoon. Yeah, so like that's 2 orders of magnitude larger. I think it's actually 3 orders of magnitude larger, right? So you're almost, it's 1,000 times slower. When you exhaust RAM and you have to go to, the next potential area is non-volatile memory, and this would be like SSD storage, but when it's set up in a set up kind of in a volatile manner, you can maybe get 300 to 400 nanoseconds of latency out of it, and then you start getting into SSD and other things. So the point is,
weird
the reason
question.
why
swap space would sit on that SSD space, maybe NVMe, where if that's where you were storing, but ultimately, like for that extra download memory with Linus Tech Tips, it's sitting on NVMe, SSD, or HED, or maybe even slower because it's internet based.
Yeah, so his stuff is going to be like when we get up to accessing, NVMe or your solid state drive, we're talking about microseconds, right? So now we're talking about tens or hundreds of thousand times slower than registers and like thousands of times slower than main memory. And what Linus Tech Tips did was they mapped internet storage as swap space. And now we're talking seconds, right? In order to access a page of memory out of this network storage. But in theory, you have a potential infinite storage space, right? But that's not really RAM, right? You're not really downloading RAM. It's just storage. CXL lets you download RAM. And I mean that sincerely. Like you can, at runtime, like these devices do not exist yet, but they will exist in the next 1 to 2 years, and then probably start to see hardware samples come out, and we'll probably see the first real device, and we'll talk about what some of these devices are, that will let you, at runtime, add more RAM to your PC that it exists outside the chassis.
So as a question, though, because I've heard this before, in a year's time, we'll have flying cars. I've been promised that a long time. So that's the question: is like
there's real hardware out there.
There's real hardware and all of that.
I'm not going to talk about that stuff in particular because I'm not going to play the game of what's embargoed and what's not embargoed. So I'm just going to say this hardware exists, and let me put this to bed. Intel and AMD have said they're shipping CXL compatible processors, in their next generation, right? So this is coming to fruition.
Getting to the core of the problem. Like the core of the problem is that when you're running VMs, processes, anything like that, you need more RAM. And regardless if you we'll say if I have a big ESXi cluster, like a big VMware cluster to spin up systems, I am still going to be limited about the amount of RAM that can physically sit in that chassis. Is that correct?
So there's, yes. Well, no. Because some of this RAM will live in a separate chassis.
No. I'm not saying where the problem. I'm saying the problem we're having right now.
Today. Yes.
The problem today.
The problem today is there's, and I'll say there's 2 problems. One is if you are actually utilizing all of the capacity, you will, I was doing the back of the napkin calculations. If you have like a terabyte of RAM and you have 64 cores, I think it comes down to I think it's like 8 or maybe 16 gigabytes of RAM per core. And maybe that's sufficient to you if you're running little apps in each of these things. Maybe you have a 4-core machine that has 64 gigabytes. That's a lot, right? But for certain workloads, that's not a lot. For future AI model workloads, for genomics workloads, for things, things that the future is going to be built on, all that matters is how much memory you can have so that you can get that ultra low latency access to data and not have to go to storage class memory, stuff like SSDs.
Yeah, so again, I'm going to get to the question is, why can't that happen now? What is the actual limiting factor? Like, what is the problem this solves?
One is capacity. And the other one is bandwidth. So everyone's probably opened up their PC at some point and upgraded their RAM of some kind. And there's always what, like 2-4 slots, right?
Yeah. Maybe in a
Well,
server you can have a lot more than that, but
maybe you
you're
can have a
still
lot more than that. And there's some number of channels between the processor and those slots that allow them to access it. And there's memory controllers there. I'll say the third factor is cost, and we'll talk about that in a second. But so bandwidth with those channels, if you populate every single channel with the highest capacity thing, and you get up to that 1 terabyte of RAM inside of your chassis, that's great. You can get really fast access to that stuff, but you have a limit on how much you can access concurrently.
okay.
Right? Because you've saturated the memory channels. And so if you have 64 tasks running on your 1 terabyte machine, and every single one is trying to access all of its memory all at once, the machine's going to slow down anyway. And so maybe you'll get better latency access, but you're still going to end up having to wait because the bandwidth is crap. So you're fighting against multiple things.
And that limit is based on the processor. So the processor only has like a limited number of channels to interact with the RAM.
Yeah. And I mean, like at a certain point, it gets, when you get down into the electronics of it, right? There's only so many of these memory controllers that you can jam into the processor without it getting massive and, absurdly expensive. And if you've seen the die space of modern processors, they're getting chunky, man. Yeah. Even with the 3D designs, they're getting big. So the third part of this is, I'm not going to go into the OS level stuff, but the third part of this is cost. Have you looked at what RAM costs today? DDR5.
Not recently, because I don't really want to start crying, but also like
this is like I think the last time I looked at it, it was something like $5 per gigabyte or something like that. And which doesn't seem like a lot, but when you compare it to storage class memory, SSDs, a NAND flash gets down to like 25 cents per gigabyte, right?
It's not
and so
bad. With the chip shortage, it feels
it's not
like
bad.
A lot higher.
It's not bad if you're buying 1 terabyte of RAM. If you're buying a petabyte of RAM, it's huge, right? Like this is where the capacity issue gets into place because, oh, great, we can just add all the RAM we can possibly ever want in the world. Yeah, but one, who are you getting it from? And two, how much is it going to cost you? Because the more you buy, it does not get cheaper the more you buy, at least not until the fabrication facilities catch up and all those things. So there's all kinds of tizzy in the market as to, how can I increase capacity in a financially stable way? And I have mountains of DDR4 left over. Can I use that mountain of DDR4 and do something useful with it? And, can I actually make it so that I can solve that bandwidth problem? Because we're saturating the channels already. And so CXL, Compute Express Link, is this technology, is built, like I said, it's built on PCIe. And the idea is I'm going to have these expansion cards that do one of three things. And the first case is like SmartNICs and like simple things that are just transferring data from outside and into the PC. And I want to be able to have fast transactions between the PCI bus and so like these things already exist basically, or they're simple devices like retimers. We're not going to focus on that one. There's the memory expander case where this is I have a PCI card with a bunch of RAM chips just plugged into it, and then I plop it into my PCI port, and now I have a NUMA node that I can just treat as another chunk of RAM. And I'll get probably about in a 2-socket system, it'll be like one socket accessing the other socket's memory is about the latency. But, and this is, go ahead.
No, I was going to say, is that you're starting to lose me. And this is why I want to pause for a second. It's saying like, you hit me with 3 problems. Problems exist is like you have physical expansion, or do you have something to add before I jump back in?
Right. So what I just described to you doesn't actually solve. It doesn't. We're not downloading more RAM, right?
Yeah.
Where's the downloading more RAM part come on? The download more RAM part comes from. Imagine I have a chassis that has no compute on it. There's no CPUs on it. Maybe there's a controller or whatever that lets me change the configuration of how you access this thing. It's just full of DDR5. Right? It's got some ports on the back, and it plugs into another chassis that has the compute on it, and it's connected over fiber, so it's really low latency. And at runtime, you run out of RAM in your chassis that has 1 terabyte and says, I'd really like another terabyte of RAM. So you contact this other chassis you're hooked into, and you say, provision me a terabyte of RAM. It does the thing. You online the memory in your operating system, and boom, you have 2 terabytes of RAM. Now, granted, it'll be slower latency, but it'll still be faster than going to storage.
There's two. Well, what you're describing sounds on the surface like that it's not that hard of a problem. Again, on the surface, there's 2 pieces. One, it's like, it just sounds like a SAN or a NAS for memory. The kicker here is, as I'm sitting here, again, having heard about this and thinking about this, for me who's in security, this sounds like a security nightmare, because I think of things like, like Heartbleed or any number of memory dumping techniques. If I can break out of, we'll say, for lack of a better term, the sandbox on this thing, I now have access to RAM for all these other servers.
Yep. And security is a huge concern in this new world that we're entering. Like, just to really, I'm gonna hammer one more thing home, and then we'll move on to some of the security aspects. This idea of dynamic capacity with memory is exactly what you just said. It's like a SAN, right? Where I can plug additional hard drives into a SAN and just bring them online at runtime, and maybe reconfigure things and allow someone to partition drives back and forth, change permissions on which box. Yes. Prior to today, that was storage class memory only. So yeah, you're exactly right. This is like memory going through what storage went through with SANs and other devices. And there's like, it gets more complicated than just like, it's like a SAN for memory. There's going to be all kinds of crazy devices like accelerators that have onboard RAM. You configure the thing, you pass data back and forth, and then you change who actually controls it. Like, in one sense, the CPU would control it for a little while, and then you would pass ownership over to the accelerator. And so now the accelerator doesn't have to ask CPU permission to do things with it. And so there's all kinds of performance increases. I don't want to get down in the weeds on that, but you're right. There are all kinds of security concerns in this new world.
I'm also just thinking though, like, oh my gosh, like, so we're not going to be able to go into some of these questions. I have so many questions.
I'm an open book, man. I'll tell you what I can. But
one of the things I'm thinking about though is the redundancy gained from a system like this for critical processes. Like, typically, when normally, like, you have multiple servers doing, like, failover and backup. Like, if I'm doing something critical with a set of keys that I cannot have fail, you could almost have like we'll say a delayed set or a mirrored set of memory, which is delayed, where you go all of a sudden, like, instead of getting a blue screen of death, like, to overgeneralize it, instead of giving a blue screen of death, you can then revert back to where memory just was, because you have a whole separate, like, copy of it, and then resume from there.
Yeah, like a fast snapshot in memory. That's definitely one use for it. Or, I mean, if you look at it in the RAS case, like you were just saying, recovery. If you're able to detect portions of a piece, an individual DIMM are starting to go bad because it's ECC RAM, you'll get warning signs that you're starting to collect errors. Once you hit a certain watermark, you could just decide, online another chunk of RAM, move everything from this DIMM to that DIMM, and just offline that DIMM and mark it as broken, and then somebody can come along and pull it out and put a new one in without shutting the machine down.
Does this? Oh gosh, because I'm thinking also too, it's kind of like, is it Backblaze? There was like a backup solution, not a sponsor, but like there was a whole like backup solution online, which most of these ones just terrify me, to be honest. But I think it was like Backblaze who came out with effectively these chassis, which were really, really inexpensive to put together. And it made use of all these like 2 terabyte, 5400 RPM, like slow drives, because they could be used for archiving purposes, and it breathed new life into it. It sounds like this would do the same thing with memory, because now it's sort of inexhaustible. The memory, I can use the old stuff to get the same speeds almost.
Just download more RAM. Just download more RAM. Like I keep saying this over and over at work a bit. I'm just like, guys, this is amazing. Like we're downloading RAM here. This is awesome, right? Like this is a 20-year-old meme come to life.
The problem, again, kind of like to summarize it, is like you have storage issues, you have cost issues, you just have like general like allocating it issues. And one of the going,
yeah. I was going to say, just think of like some of these AI workloads, some of these genomics workloads, trying to map genomes, trying to crunch, fold proteins, all these things. Some of these things are compute bound. A lot of them are memory bound. And by that, I mean, they're working with these. All right, let me put it in the terms of security. Password cracking, right? There's a bunch of different ways you can do password cracking. One of the oldest methods are rainbow tables. The problem is that once the rainbow tables get to be beyond a certain size, the lookup times become so dramatic, and the crunch times become so dramatic that you're better off looking for, or the space becomes so huge that it becomes super bad. But now you can start to look at, well, if I have a petabyte of memory available to me at this lower latencies, I can start to look at, well, what can I do computationally that I could expend, half a petabyte of memory in order to speed up the computation because I've pre-computed something, right? And so that's the idea. And if I didn't have that scale of memory available, I would be stuck having to do maybe the slower but more reasonable compute heavy workload that isn't going to be memory bound. And so there's always going to be this race in computer science between I'm saturating the compute versus I'm saturating the memory versus I'm saturating the storage class memory, and then having to figure out bandwidth and all those things. What nobody and by no means is this a new problem, right? People have been trying to solve this, we'll call it composable memory problem, for about 30 years. And there have been multiple attempts at this. Like I said, even Linus Tech Tips had a video that showed an old PCI card with DDR4 or maybe it was like DDR1 slapped to it. And it was over a decade ago that this card was made, with the idea of increasing bandwidth. And the only problem is, at that time, it was a PCI bus and as opposed to a switch or PCI lane. So you may have heard like dedicated PCI lanes. The reason you get bandwidth out of this system is because in a lot of cases you have dedicated PCIe lanes directly from your CPU down to these endpoints, these cards that are plugged in. And in those cases, if I make two requests to two different devices on the PCI complex, I'm not going to run into each other, right? I can get both of those done at the same time. On the old PCI bus, it's a bus, so you got to take turns, right? Which means you would get trash bandwidth as a result. But that's not the world we live in anymore. So we can have dedicated lanes. So I would expect over the coming years that you're going to start to hear CPUs no longer, like we've already seen this where some CPUs have like 128 PCIe lanes. We're going to start hearing like absurd counts of like 256, 512, 1024 PCI lanes. And it's all going to be focused on that because they're going to try and parallelize. Like, I don't think people really comprehend how big this software defined memory movement is going to be, because this is really one of the last areas within hardware that I've seen that is not software defined yet. We've figured out how to plug accelerators in and define the architecture of that. That's your graphics card, right? So we can, even at runtime, plug a new graphics card in, pull it out, reconfigure it, do all these things. So these runtime configurations of accelerators that kind of already exist. But memory has been this like last holy grail. If we can figure out how to do that, well, all of a sudden, what do computers look like in the future? If I can have my memory completely separate from my compute, completely separate from my accelerators, well, do we go back to the days of just having trays of CPUs plugged into this really tiny chassis and then just having a bunch of wires connecting to a bunch of other boxes? Is that what a server looks like in the future, as opposed to dedicated dedicated motherboards with all kinds of integrated stuff? Does everything just connect over PCIe in the future? And yes, the security implications of this are crazy. Because I said you have, in this simple case of pooling memory, right? Have this chassis that's just full of memory, and then at runtime there's a configuration module that you contact and maybe download more RAM or maybe upload RAM. Uh, that configuration module has the keys to the kingdom to a lot of other people's data, right?
Mm-hmm.
So if I have 10 chassis connected to this thing and they're all chopping up different memory, and one of those chassis gets popped, and one of those chassis has access to the control plane and is able to, pop this device and be able to get, shell or root or whatever, because this pooling device is probably just going to run Linux. Yep. If you pop a shell device, get access, and you have the ability to do administrator level stuff, what's to say you couldn't map memory that's already mapped into another device?
That one I'm less worried about. And I say that because like we have solved that in so many other ways. Like whether it's virtualizing, whether it's containerization, like I use like lambdas as an example. Like you can't, like if you spin up a new lambda or something like that, you're not going to be able to access like RAM inside like where someone else used it. So like I would think that for its speed, there's going to have to be all these wiping capabilities saying, okay, I'm now reallocating this. I now need to wipe this piece before I give something else access to it.
So all of that is flushing out, and all of that is in the spec. They're talking about having, properties of these hardwares being able to say like, oh, when I turn you off, auto wipe or whatever. So all of those things are being built in the hardware. The thing I described is not that. The thing I just described is I have a machine that's actively utilizing a piece of memory in this chassis, and now I'm going to also map that same memory into another device while it's mapped concurrently, right? Which is a technical and electrical possibility. Like this can be done. It can be possible to share a single chunk of, DDR DIMM across two of these devices. There's nothing that prevents it electrically. You just need to, like this, a device like this will probably exist as a simple pooling device. The concern is, at runtime, if I pop one device that has access to the control plane and then I change the switch configuration to have two devices now pointed at the same RAM, I could have a quiet snooper off in the corner who just reads data from that and just pulls whatever.
Hold on, though. Like, oh gosh, you talk about that as a security vulnerability. Think about like it's like having a span port. Like so on like a network switch, you have two ports spilling the same traffic, so I can pull it off for logging. I can pull it off for any number of things. You think about the security ramifications, not as an attacker even, but as a blue teamer to be able to watch anything as it happens in memory.
And this is where it gets kind of difficult because like I say this as a security geek. I'm like, this is really interesting. This is a really interesting, a threat model. As an operating systems developer, I'm like, you're never going to be able to make sense of what's on this device, right?
Well,
because
programmatically,
it depends on the computation, though, right? So, like, I could have a chassis that's mapping a terabyte of RAM or downloading a terabyte of RAM from this CXL device, but that chassis is going to be able to, if it's a multi-tenant chassis and I'm running, 32 instances of KVM or whatever, VMware or whatever, that memory is going to get chopped up all across all of these different VMs. So depending on what's actually being done in this memory and different page granularities, maybe it's like 4K, maybe it's 2 megabytes. Let's say I get access to a huge chunk of this. Maybe I get access to the entire pool and it's 1 terabyte of memory and I just download that 1 terabyte of memory. Now I'm going to go searching through 1 terabyte of memory in whatever the page resolution size is to try and reconstruct something. And some of that data is going to be non-contiguous because it's going to be shared with the onboard chassis. So like as a security geek, I can be like, this is an interesting threat vector. As an operating systems geek, I'm like, it's not going to fall out that way. You're definitely going to be able to access some data. And if that data is like financial data, right, then that's going to be an issue because 4K is a lot of memory out of a financial database. Like you're going to have enough information probably to reconstruct.
The thing which I'm laughing about is like memory has been theoretically the last bastion of hope for unencrypted data. Like private keys need to sit there in order to decrypt. I feel like I had this thought like while you were a thing where it was where I started giggling and was going like, it's turtles all the way down. Like I can solve that by adding a layer of encryption into memory, which then I'm going like, wait, how do I decrypt this? Wait, I would have to have maybe like it would effectively like be like like TPM. This is like what TPM was meant to like, or Secure Enclave or any of these chips was like. I'm going to randomize the memory. I'm going to encrypt the memory on the fly using this other chip, so that it's not a. Oh gosh, it is so like it solves so many problems, but it creates so many new ones that you're going to now have to solve.
So, and this is where it gets really difficult. And like the rollout of this is going to be relatively slow, at least at this scale. The scale that we're talking about, where I have like a petabyte scale CXL device, it's going to be a while before that shows up in the market. I think in the next year or two, you'll be able to buy CXL memory expanders that you could slot 2 terabytes of DDR5 if you can afford it into your home PC. Like that's going to exist. The next generation Intel and AMD processors are going to support that from press releases that I've seen, right? So what you've just described is, yes, we can solve the data exposure problem by encrypting it. But remember, I showed that pyramid at the beginning that shows here's the latencies of these different classes of memory, and RAM DDR is about 140 milliseconds, right? And the CXL memory, if you want to bring it back up, is, local CXL memory should be about 160, 170 if it's sitting directly in a PCIe slot. If it's across one hop or behind one PCIe switch, where it's like, if I'm going to one of these chassis, the upper end of this is probably going to be 250, maybe 300 nanoseconds of performance. What you just described in adding encryption into this, there's no free lunch. You're going to add latency because you've got to encrypt and decrypt. And so you're going to have different classes of storage, and you're going to have different security domains where you're like, well, anything in here is going to be unencrypted, but anything outside this domain is going to be, it's going to create a whole new layer of just like, who the hell knows what kind of security problems we're going to see in the future with this. And it's going to be interesting. And to the CXL Composium's credit, they're talking about it now, and they're talking about it in terms of the spec. That's why a lot of the hardware specifications say, what do I do on reboot? What do I do on soft reboot? What do I do on just device reset? What do I do when I deallocate this thing?
I'm still intrigued by the fact that you can, using something like this, it breathes new life into old hardware. Like, for all these, like, we'll say like the cloud providers, the AWSs, the Azures, especially when you allocate, like, I need my memory to be the speed and things like that, all of a sudden, all this old hardware, they can now breathe new breath into. Like, old drives through Backblaze, through Glacier, and all of these other things. We don't care about speed because it's used for archiving, and we're not using tape drives. Theoretically, some places are using those and things like that. Mostly, though, the storage is so cheap for that, you can just archive that stuff off using cheapo drives. You can now do that with memory, and that is fascinating to me.
Yeah, so I mean, like, that's the thing is, and right now we're just talking about volatile memory. There's gonna be all new kinds of classes of memory as well. There already exists non-volatile memory. There NVMe attached NAND, right? And so those can be used like volatile memory with a higher latency, or you can use them as persistent memory and be able to offload some of your things to that area. And it's at a higher cost than maybe SSD class NAND in terms of like price dollars, but it's lower latency. And so you're going to see, like, that's why that memory pyramid is so interesting. As memory becomes like your memory fabric, if you will, becomes more software defined, you're going to have much more complex hardware systems to have to try to secure. And to me, that just sounds like there's a lot of money in security in that area in the future.
No, we wouldn't create new problems just to be able to solve them.
Well, I mean, CXL could stand for cyber something, which means, more money.
Probably does. We do love our acronyms. You had another picture though, which was like a flow chart. What was that describing?
Sure. I'll show that. And this basically just explains the bandwidth problem. So you're probably going to have to increase the size
Yep.
of this one a little bit. So for our listeners, I am looking at a PCIe complex, and the idea is you have this root PCIe complex attached to a CPU, and that root complex is going to have downstream ports. And that downstream port is going to be one of a few things. It can either be an endpoint, like your GPU directly plugged into a PCIe port. It can be an NVMe device directly plugged into a PCI port. And this is what we're talking about when we say lanes. You know, some of these endpoints on dedicated lanes have a dedicated downstream port off of this root complex so that you can run them in x16 mode. Where it gets complicated is you can also have a PCI switch off of this root complex where you have multiple devices under this switch. And that could be like old school PCI endpoints. It could be multiple PCI endpoints on top of that. And the reason why you do that is because you just don't have enough lanes to support all the devices you want to plug in. And that switch adds latency. So even within your own chassis or your desktop, you have different classes of PCI ports that you can plug into. And that's why when you buy like an NVMe drive, if you look at your motherboard specifications, it'll tell you capable of supporting one NVMe drive, even though you have multiple ports. And the reason for that, what they're really saying is like, this is the slot that has the dedicated lane. So if you want the best performance, plug it into this slot. Otherwise, it's going to be below that switch and it's going to have higher latencies and less bandwidth because it has that switch below that could have a bus below it as well. It gets more complicated. And then beyond that, you know, off of that switch or off of one of these root ports that have dedicated lanes, you could have a card plugged in that maybe has fiber or copper that goes outside of your chassis, connects to another chassis, and then that is connected to a PCI switch. And that's basically the idea behind CXL and remote access to memory in another chassis. And then the cool thing is, imagine, and like this is not the way things are set up right now, and PCIe is certainly not set up to do this yet. And CXL is kind of an attempt to do this. Imagine you have two servers where you want to access, you know, I have four. I didn't buy one server with 4 sockets. I bought 2 servers with 2 sockets. And I want to map directly chassis 1 or chassis 0's socket 0 memory into chassis 1's socket, you know, 2 or 3 memory. And I want to be able to cross use this at similar remote CXL latencies. So not only talking about you're talking about having a dedicated device that has all of these memory arrays in it that potentially have access. Now you can talk about just adding another blade or rack or whatever to your compute, and all of a sudden you can just do remote access into somebody else's chassis into their memory. And some of these things already exist with things like remote dynamic memory access, RDMA, but the latencies are really high. Because you're using I/O, you're usually going over network cards, you're usually going over. Mm-hmm. Now the electricals on this are designed to just be direct access, which is kind of crazy to think about.
So you're starting. Some of this is going way above my head. Like, what has been the weirdest and hardest problem to solve with this? Because we talked about the problems you were looking to solve. A lot. This solves many of them, not price and stuff. Well, even price, because you can do like cheaper memory.
Do you mean make what's this the hardest?
Yeah, to make CXL like a reality, we'll say, what has been the struggle of it? Has it been just hardware? Has it been software? Or has it been like consensus among everyone trying to figure it out?
Now, granted, I'm probably not the person to ask that question, but from my view, the hardest one probably did seem to be consensus, because if you look at the design of CXL, it's very PCI based. Right. But prior to this, you had people developing memory expanders, you know, all the way back 15 years ago. You know, these first memory expander cards started showing up 10 years ago, which means they started developing them 3, 4, 5 years prior to that. So people have been going down this route for a while. And if you look at Optane, until Optane just died, that was like fast NAND. And you could get DIMMs of Optane and plug it in like it's RAM. And they were working on PCIe expander for Optane so that you could just plug it into a PCI slot and try to have like a terabyte of NAND in a DIMM or in a RAM fashion. And so like people have been going down this route, and then all of a sudden, probably about 4 years ago, I think, the CXL consortium comes out, and if you go look up at their website, it's everybody. And when I say everybody, it's everybody. Intel, AMD, Nvidia, anyone who's anyone in the hardware compute space is all the way behind this. So that's why when I say, when you're like, oh, I've heard, before, it's 1 or 2 years away or whatever, I was like, no, when something has this much backing and this much money behind it and this much power behind it, this thing is going to happen. What we're going to, what hardware we're actually going to see fall out and be useful, that's still a crapshoot. I think we'll see memory expanders. That's just going to happen by nature of it's useful. We're probably going to see some pooling devices show up, and those will be useful in some cases, but less cases than the memory expanders. But it's all going to be a function of cost versus capacity, which is fascinating. But yeah, I think the biggest problem was definitely getting a consensus on how to do this. Because if you think about, you wouldn't want to have AMD and Intel come up with two separate solutions to this that are non-PCI based. Whoever decided to do that would probably fail unless they got it really, really, really right. If they got it right, then everyone would just have to adopt their thing because they would run away with the market. But the hard part is there's so much risk there that I can't imagine any of those behemoths actually wanting to take that risk. And actually, I say that, but Intel's tried. Intel had InfiniBand. AMT has like Infinity Fabric or something like that. All of their supercomputer scale things have tried to do some level of software-defined memory and memory disaggregation in the past, and all of them have fallen towards this PCIe design, which is cool. This is the thing I want you guys to walk away from a little bit is like, this is really supercomputer level fabric, quote unquote, technology finally making its way towards the desktop, because these types of fabrics have existed at the HPC and the supercomputer level for a while.
Now, you've mentioned it a few times, and I never realized this technology would actually, like, why would I care to have it in my desktop? Because I've always envisioned this like servers and cloud computing and supercomputers, but you've now mentioned it like twice in the desktop. Why would I care to have it in my desktop?
You won't care to have those pool. I mean, maybe you might, but the pooling capacity of being able to download RAM, you might not care about having that on your desktop unless you're doing big graphics compute, right? Like if you're doing, I mean, in some argument, like it's really the reason why you would want it in your desktop is capacity. I want to be able to have a terabyte of RAM so that I can look at some of the simulations that I'm doing in live real time. I think I was looking at, somebody had a simulation from NASA of one of their rockets or one of their missions going to Mars, and you could actually play frame by frame. And it wasn't like a video you were playing. No, you were running the simulation frame by frame of a lander going to Mars. Well, that model was like terabytes of data. And so if that's sitting on your machine and you've got to go access the whole model to do this, each frame is going to take you a really long time to compute. If you just have access to this class of memory, accessing all of that data to do these things is going to be much faster. Even, I mean, in the AI workload case, you training the AI is one thing, because you might need a petabyte of data to train the AI, and you're going to get a model out of it. But that model might still be a terabyte in size, right? And so if your desktop only has access to 64 gigabytes of RAM, having a terabyte AI model is going to be a pain to run that model locally. But if you have access to a terabyte of, we'll call it slower class memory, but faster than storage class memory, it gets to be feasible to use that 64 gigabytes of RAM as a fast tier, or we'll call it an L4 cache, right? And just like tier memory between the slow and this fast memory. And so maybe you're going to get worse performance than you expect, but you'll get faster performance. You'll be able to do something as opposed to nothing, right? In these classes. So it's going to change the workloads that you could potentially run on your desktop.
I imagine the other place it's like I'll feel the impact. Like most normies who are not like have a supercomputer in the back of their house, the way it's going to impact us is not necessarily like, oh, in my desktop or anything like that. But when you're trying to spin up like a DigitalOcean Droplet, an AWS system, like I was reminiscing with someone yesterday about this. My first laptop I ever bought was I think it was either Sagar or Seeger, Sager. It was like an off brand at the time. I don't even know if they're still around. It was $2,600. I had to save all of my pennies in high school in order to get this thing. And it was like a Pentium 4. Like it was nothing great. And it had like I think it was like a gig of RAM. And it was like, whoa, this thing so fast. And I remember when like AWS first came out, and AWS, like even a cruddy system was stupidly expensive. And now the price,
it's still expensive.
No, but like, sure, we'll say sure, but like I've been playing around with Firebase lately, where it's like I legitimately am running 4 apps in it for free, and now like just recently I crossed a weird tier because I want to have like 4 Lambda functions running with a minimum instance at one. So effectively that's 4 processes continually running all the time. Like, and that cost me $1. Point being, like AWS is like I can have a system for $3.50. I think there's like on light sale it's $2.50. It's a decent system. It's like a one processor, half a gig of RAM, whatever. It's cheap. And what ended up happening over the years is these systems have gotten awesomely cheaper and cheaper and cheaper and cheaper. And the processing has been increasing slowly at the same price, but memory has stayed pretty consistent.
So let me toss this idea. Go ahead.
I was just finishing the thought. Is like it seems what's going to end up happening is memory is going to either systems are going to get cheaper, or memory is going to become more prevalent, where the high memory based systems are going to become cheaper because now this is a possibility.
So yeah, and that is a key observation. But I'm going to take it one step further, because your mindset, because you haven't really seen or read the spec or seen some of these things in action, is still based on the idea of I buy a piece of hardware and that hardware's configuration is static, right? So you can imagine in the AWS cloud, when you rent an instance, you get a 4-core instance with 64 gigabytes of RAM. You can imagine a chassis somewhere where maybe you can just chop up a corner of it and you're getting 4 of those cores and some chunk of the RAM allocated to you. There's a specific problem in this space called memory stranding, where if you allocate 64 gigabytes of RAM to you, well, how many more instances can you spawn on that chassis, right? Because you have dedicated 4 cores and you have dedicated 64 gigabytes. Let's say that there's 256 gigabytes there. Let's say another person comes along and wants 2 cores, but they want 128 gigabytes because they're memory bound, not compute bound. Whatever, doesn't matter. We have this class of problem within memory management, where we used to call it fragmentation, where all of a sudden you couldn't get access to a contiguous area of memory because everything's so fragmented. And so that's what you would do to your hard drive, is you would defragment it in order to free up space and make it faster to access stuff. Well, imagine a world where you rent a 4-core machine with up to 64 gigabytes, but you're only using at any given time, like 8. And as long as you're only using 8 gigabytes, you're not being charged for the other 56 gigabytes, right? Because somebody else on that chassis could use it, right? Mm-hmm. But now it gets even better. You can rent a 12, half of the cores on the machine and up to 2 terabytes of memory, and only use up a chunk of the local DRAM, so they could launch more instances. This is the core idea behind software-defined memory, is I want to be able to free some of that memory that isn't actively being used and replace it with maybe slower classes of memory that isn't really going to change much in terms of your performance. And maybe you, as the customer, get a discount on that. So now you're only paying for what you use as opposed to paying for a static instance somewhere.
It's interesting because what you're saying is I guarantee, I understand the guarantee AWS will go this direction because right now they have spot instances. I have used them successfully for security for years because I can get like the GPU, like for instance, like the GPU ones. I want to do password cracking. I want to do password cracking over this engagement lasts a month. I don't have, like, I actually have a GPU. Point being, I want to have a giant amount of GPUs. I want to do CUDA cracking, all of that stuff. Instead of paying like $3.50 per hour, I can pay like 30 cents because I do spot instances. Now those spot instances allocates the entire thing. This whole idea of doing like you only pay for what you use doesn't exist within the AWS right now. It does because you allocate it that way. But paying for actual usage is fascinating. Like, that is fascinating.
No, it's definitely an interesting business case. And I mean, it gets more complicated. Is that the way it's actually going to fall out? I don't know. I do know that the dynamic expansion and contraction of memory is an interesting use case to solve this stranding idea. Because I think Microsoft Azure, and I think Meta also came out with a paper. I think it was mostly Microsoft, said they did a survey of their cloud, Microsoft Azure, and showed that for all of the instances that are allocated, those instances tend to use on average 50% of the RAM that they provisioned, which means if you think about it in terms of the size of Azure, the amount of money that they have to spend on RAM for it to not be used is absurd. Like we're talking too, like tens or hundreds of millions of dollars, right?
Where the other piece of this though too is like from a development perspective, like let's like bursting. This is where like Lambda solved so many things. Is I can say, okay, for this one API call, this singular API call, which does this one thing, anytime someone hits that URL, that REST call, spin up, like either warm up, cold boot, whatever, depending on what state it is, run this one thing and then die. Like just run it and be done with it. The fact that you can recapture that memory and actually like, my point is like, you never know how much RAM you need when your applications have these emerging properties. When they get bigger and they get more complex, you really don't know how much. And you could have it dynamically allocated going, okay, I need a little bit more, I need a little bit more, I need a little bit more. Again, set a limit on it. It solves a really cool problem because now you don't have the stranding idea and it can be dynamic. You can download more RAM and have it dynamically added on.
I mean, fundamentally, at the end of the day, like I keep going back to this idea, this is just like downloading more RAM because at the end of the day, it's still RAM. It might be a little bit further away. And you know when you think about it in terms of downloading more RAM, what does that actually mean? It means you get access to RAM at speeds that make your system faster. Well, that's what we would be doing in this case. So you're just downloading more RAM. It's amazing. And like the funny thing is that the CXL specification is written in a way such that technically speaking, you could do all of this over carrier pigeon because that's the way all of these specifications are written, right? So imagine, in theory, you could map RAM hosted in Google Cloud. Right? It'll be really bad latency. It'll be just like storage, but it'll be RAM. But and when I say that, I mean it's not going to be a file on a disk somewhere. It'll be an actual hardware piece. It'll be an actual DIMM.
Yeah, I mean, I feel like that one less so. Like, I don't think you're going to hit it. Like, I don't see right? I don't see a practical use for that because at that point, might as well just plug in a cruddy drive or do like the Linus Tech Tips. Like, I'll just use swap space effectively. Like,
no, the point being that like if Linus Tech Tips were to remake that video where they use Google Drive swap space, in theory, the Google Drive swap space could be like the Google RAM drive where it's actually backed by RAM instead of a hard drive, right?
What's so nuts about this too is we have this like we have this weird pendulum like a shift. I remember like AOL dial-up. You're like, ba-doo, ba-doo. You're like,
Yeah.
yes, 28.8. It's a good day. Like, all of a sudden, like when we get faster speeds, you get, gigabit, you get 10 gigabit. All of a sudden, like, maybe I will download more RAM because now I can actually take full advantage of it.
Well, and this is a lot of software right now, and this is going to be the difficulty moving forward. And I think this is where a lot of security issues are going to show up. A lot of software right now is actually very memory conscious, right? Because it thinks of memory as static, right? I have 512 gigabytes of RAM. What can I do most efficiently in this situation? So maybe it works on one chunk in one area while it's paging in a ton of things from the SSD at the same time. In order to like set up phases of computation, right? Well, all of a sudden, that's not the most efficient way to do your job. The most efficient way to do your job is to just put it all in RAM and start chunking through. And if you run into that limit, you just expand, right? And I've already done some experiments to show that, like, yeah, that's a feasible way of doing this. Like you have a longer spin up time, but once you hit the capacity that you actually need, like it's smooth sailing after that, because it makes sense. It's just like swap space, right? Like, but at the end of the day, people are going to try and take some of those old pieces of software and make them work the way the new stuff works with this dynamic capacity idea where your max capacity can change. And I think we're going to see a lot. I imagine in the next 2 or 3 years, not imagine, I know something's going to happen where somebody takes one of these systems, they expand it to make it work this way. And there's just going to be this like off chassis RAM that they use. And, someone's going to have shared mapped access to it. And all of a sudden it'll be like, well, what do we need? What are we going to do about this? It's going to come out as a CVE. But the problem is, and I will wave this away a little bit. The first CVEs that you come out and see about this are going to be like, well, if you have physical access to the machines, you'll be able to do this. And it's like, yeah, whatever. Right.
Yeah. It's some of these
but
ones.
As this creeps in, the thing is as it creeps into the cloud and as you have these shared instances and multi-tenant instances, these things become more and more and more important to solve for.
I think that's probably is going to feed into a topic me and you need to talk about, which is this whole, I have gotten so disillusioned to CVEs and security in general because there's one, now that I'm getting into like some of this development for my own software, there's like one with Quill.js, which is legitimately like just a rich text editor for JavaScript. That's what it is. And someone's like, oh, it's a cross-site scripting vulnerability. If you get raw access to the database and can insert whatever you want, it's like, yeah, you can also just run SQL commands. You can also do anything you want. And it's just like these weird CVEs, but they could get filed, they can accept it. And it's like, I have just lost most faith in CVE in general at this point. And mostly all of security. And with that, what's your parting thoughts? Is this the future? Is this where we're going? Is it worth spending your life pursuing?
About my life? No. my spending my life pursuing what's worth spending my life pursuing? Spending time with my wife and dog. That's worth my time, right? But yes, obviously I work in this space, so I think it's a valuable space to explore. It's going to be really interesting. I'm very fascinated to see how hardware is going to flesh out in the future. And of course, as always, delete computers, return to monkey.
This was a really technical conversation for me, especially when I'm like, at one point I'm going, oh, wait, what is he talking about right now? But it was good. It was great hearing about what you're working on, especially this one, because it's a next phase of computers, which we haven't got to yet. And I am interested to see where it comes out. Thanks for joining us on a Saturday. If you're listening, thanks for listening. And as always, hack on.